Hello everybody. Today we will be talking about fast Fourier transformation. This is the second lecture in a two-part series. In this lecture we will actually delve into the details of the algorithm. We will be studying fast Fourier transformation in the context of polynomials. We will first of all treat a polynomial as a vector in a suitable vector space. We will understand this vector space a little bit. We will understand, we will look at an alternate basis, the Lagrange basis in this vector space, and we will show that transformation from the standard basis to a suitably chosen Lagrange basis can be achieved via the application of the fast Fourier transformation algorithm. So, this will be the context in which we will we will study the fast Fourier transformation algorithm. Let us first understand what we mean by the polynomial vector space. Consider a polynomial p of x. It can be written in its standard form as a0 plus a1x plus a2x squared plus and so on up to a sub m x raised to the m, and this is a polynomial of degree m. And to store such a polynomial in a computer, we would just store the list of coefficients. So, the vector a equals a0, a1 and so on up to a sub m is called the coefficient representation, and this will be the form that is suitable for computer storage. Now, let us consider the set uppercase P sub d of all polynomials of degree m that is upper bounded by some d, and for simplicity, for convenience, we will assume that d is a power of 2. We will later explain why this is useful for us. For now, we will just keep in mind that d is a power of 2. This set of all polynomials of degree bounded by d turns out is actually a vector space of dimension d plus 1. The vector can be represented simply by the coefficient representation, and the standard operation, the multiplication operation, is the standard polynomial multiplication. Now, a good exercise for you is to verify that indeed this set of all polynomials form a vector space, and you will need to check that the properties, the 8 properties of vector spaces that we discussed in our linear algebra lecture, hold in this context. So, now given this notion of vector space, there must be a standard basis. So, let us first look at what that standard basis might be. It is nothing but the monomial basis comprising of the following d plus 1 functions. Remember, this we claimed is a vector space of dimension d plus 1. So, the basis must comprise d plus 1 vectors, and vectors in this vector space are themselves polynomials, and in particular we choose the monomials. The first monomial is x raised to the power 0, which is 1. The second monomial in the basis is x raised to the 1, and then x squared and so on up to x raised to the d. These d plus 1 basis functions can be used to construct any polynomial in this vector space. In particular, if you have if you take our polynomial p of x that we discussed in the previous slide, it can be obtained as a linear combination of the basis of functions with the coefficients being the coefficients of the polynomial in the coefficient representation. In other words, P of x is equal to the vector product of B of x times A transpose. So, now let us look at the problem of polynomial interpolation. In this problem, we are given some number of points in the 2D plane. Each of these points has a unique x coordinate. The points are x 0, y 0, x 1, y 1 and so on up to x sub d, y sub d. So, here is an example of such a situation. We are given 4 points in this example. They are marked in red, and the table here gives the x and y coordinates for each of these points. Our goal is to compute a polynomial P of x such that for each of the x sub i's that we are given, P of x sub I evaluates to y sub I. So, here we have depicted the actual polynomial that evaluates to y sub I for each of the corresponding x sub i's. And there is this polynomial that we have here that is drawn out, and we also have the expression for the polynomial in this example 4x cubed minus 2x squared minus 3x plus 4. The points x sub I are called the interpolation points, and the polynomial that satisfies these conditions, that is the polynomial that actually goes through all the points, all the d plus 1 points that we have mentioned, is called the interpolating polynomial. This is interesting because there are some natural questions that arise. Does such an interpolating polynomial always exist? Could there be many such polynomials, or will there be a unique such polynomial? These are all interesting questions and also important questions, and we have an important theorem in this context. The uniqueness of interpolating polynomials. So, given d plus 1 distinct points, and these are x 0, x 1, x 2 and so on up to x d, these are interpolating points, and arbitrary values y 0, y 1, y 2 and y up to y sub d. Our claim is that there is a unique polynomial P of x of degree at most d, such that P of x sub I evaluates to y sub I for all I going from 0 to d. Now, this theorem does not talk about polynomials of a degree greater than d. If you consider such polynomials, then you could have many polynomials going through these points. However, if you restrict yourselves to polynomials of degree at most d, then this theorem provides us with a guarantee that there is a unique polynomial that does that interpolates those points. And the proof is not very hard, so we will look at the proof. So, for the sake of contradiction, let us assume that there are two distinct polynomials P of x and Q of x, both with degree bounded from above by d, and for both of them they evaluate for each of the interpolating points x sub I, they evaluate to the same y sub I. So, P of x sub I equals Q of x sub I equal to y sub I. So, we want to show a contradiction, and towards that goal we want to we consider the polynomial r of x, which is equal to P of x minus Q of x. Now, notice that polynomial r of x must also have degree at most d, because it is simply a polynomial of degree at most d minus another polynomial of degree at most d. and this R of x must evaluate to 0 at each of the interpolating points. So, R of x sub I must is essentially P of x sub I minus Q of x sub I. They are both equal terms, and so they cancel each other out, leading to a 0. So, R of x is a polynomial of degree at most d, but it has d plus 1 roots, because there are d plus 1 points at which it evaluates to 0. But this is a contradiction, because the fundamental theorem of algebra says that any non-zero polynomial with degree at most d has at most d roots. The implication is that R of x must be a 0 polynomial, and if it is a 0 polynomial, P of x must be equal to Q of x, which completes our proof. So, let us take stock of what we have seen so far. We have seen that polynomials, the set of all polynomials of degree bounded from above by d form a vector space of dimension d plus 1, and we have also seen that a polynomial of degree d can be uniquely represented by its values at d plus 1 distinct interpolation points. So, there is this commonality that we encounter between these two observations. The polynomial vector space is of dimension d plus 1, and d plus 1 points uniquely represent each polynomial. The question therefore is whether this connection can lead to an alternative basis by which we can represent polynomials. And the answer is of course that we can, and in fact there is a family of bases called the Lagrange basis, and so that was we will take a few moments to study the Lagrange basis, because it has some interesting applications to fast polynomial interpolation and multiplication. We define the Lagrange basis for a particular set of points x0, x1 and so on up to x sub d. So, this means that there is actually an infinite family of Lagrange bases depending on our choice of the interpolating points, or the x0, x1 and so on up to x sub d. For each of these x sub i's, we construct a Lagrange polynomial. So, there will be d plus 1 such Lagrange polynomials, and these d plus 1 Lagrange polynomials form the basis functions in the Lagrange basis. And let us look at the Lagrange, the ith basis function corresponding to the point x sub I. We denote this by L sub I of x, and we require this L sub I of x to evaluate to 0 at all interpolating points other than x sub I. So, if x sub I is equal to if I equal to 2, then L sub I of x x2 should evaluate to a 1, but all other points, say L sub I of x0, L sub I of x1, L sub I of x3 and so on, must evaluate to a 0. The good news here is that the unique interpolating polynomial theorem assures us that there is exactly one such polynomial for which the above property holds. Let us actually look at an example of these basis functions. Now, the x sub I values we have taken x sub 0 is equal to 1, x sub 1 equal to 2, x sub 2 equal to 3 and x sub 3 equal to 4. These are the 4 points at which based on which we are considering the Lagrange basis. And this figure depicts the 4 Lagrange basis functions. Let us look at the basis function in the color red. Notice that it evaluates to 0 at x equal to 1, it evaluates to 0 at x equal to 2, it evaluates to 0 at x equal to 4, but at x equal to 3, it evaluates to a 1. So, this is the Lagrange basis function corresponding to x sub I equal to 3. All other x sub i's, it evaluates to 0. As another example, if you look at the green function, the green polynomial, it evaluates to a 1 at x equal to 1. But for all other x sub I values at x equal to 2, at x equal to 3, at x equal to 4, it evaluates to a 0. And so, this is the Lagrange basis function corresponding to x sub 0 equal to 1. The Lagrange basis therefore is the list of these Lagrange polynomials. So, L sub 0 of x, L sub 1 of x, and so on up to L sub d of x. Okay. A good exercise for you would be to show that this Lagrange basis is in fact an orthonormal basis for the vector space of all polynomials of degree at most d. And we will shortly show how polynomials can be represented as linear combinations of these Lagrange basis functions, and that will prove as a sort of a hint or an intuition into why these basis functions actually are an orthonormal basis. Now, recall that a set of d plus 1 points x sub I, y sub I uniquely represent a polynomial, because the unique interpolating polynomial theorem says that only there is at most one polynomial that interpolates these d plus 1 points. That polynomial can be represented as follows. This polynomial p of x, notice, will have to evaluate to y sub 0 whenever x is equal to x sub 0. It should evaluate to y sub 1 whenever x equals x sub 1, and so on. And so, this polynomial can be constructed as a linear combination of the Lagrange basis functions. Notice that the Lagrange basis function L sub 0 of x will evaluate to a 1 when x equal to x sub 0, at x equal to x sub 1, x sub 2, and so on, it will evaluate to a 0. So, when we provide this polynomial L sub 0 of x with the coefficient y sub 0, this entire polynomial is going to evaluate to y sub 0 when x equal to x sub 0. Why? Because this polynomial L sub 0 of x will evaluate to a 1, and therefore, this y sub 0 will be retained, but all other polynomials, these are all Lagrange basis functions, they will evaluate to 0 at x equal to x sub 0. Similar argument holds for other terms as well. So, when x is equal to x sub 1, this polynomial must evaluate to y sub 1. Now, all other Lagrange basis functions will evaluate to 0 at x equal to x sub 1. But when but this L sub 1 of x alone will evaluate to a 1, and therefore, since we have given it a coefficient of y sub 1, this polynomial p of x will evaluate to y sub 1. And so, this these coefficients y sub 0, y sub 1 and so on up to y sub d are the coordinates of the polynomial p of x in this Lagrange basis. The question we now ask is, how do we compute these Lagrange basis functions? And this is quite interesting. To construct the ith Lagrange basis function, we employ this technique where for each of the x sub i's we have this this multiplicative term as shown here. So, for x sub 0 we have x minus x sub 0 divided by x sub I minus x sub 0 and so on. Now, in this sequence of multiplicative terms, there is one missing term, and the missing term is x minus x sub I divided by x sub I minus x sub I. And now, this term cannot exist here because the denominator will evaluate to a 0. So, thankfully, that does not exist. But what is the benefit of this missing term? Now, let us evaluate, let us recall that this Lagrange basis, the ith Lagrange basis function, must evaluate to 0 whenever x equal to x sub 0, x sub 1 and so on, other than x sub I. But when x is equal to x sub I, it must evaluate to a 1. So, let us see how that requirement is satisfied. Let us assume x equal to x sub 0. The first multiplicative term will have x sub 0 minus x sub 0 in the numerator. So, this being a multiplicative term will immediately zero out the entire right hand side. The same situation applies when x equal to any of the other values except x sub I. So, let us look at, for example, x equal to x subscript I minus 1. You will notice that when you apply x equal to x subscript I minus 1, the numerator again will zero out, and therefore, the entire right hand side of this expression will be 0, and so we will ensure that L sub I of x evaluates to 0 at x equal to x sub I minus 1. However, when x equal to x sub I, we do not have the corresponding x minus x sub I multiplicative term. So, now the right hand side will not be zeroed out. Instead, what will happen is, in each of these fractional terms that we have, the numerator and the denominator will evaluate to the same value. And because they evaluate to the same value, they will cancel each other out, and so the entire right hand side will evaluate to 1. So, this is the reason why this formulaic way to compute the Lagrange basis works. Okay, so, now we have seen the set of all polynomials of degree bounded from above by D forms a vector space. We have seen the standard monomial basis, and we have also seen an alternative basis called the Lagrange basis. And of course, the Lagrange basis is a family of bases based on our choice of interpolating points. So, the natural question is, how do we take a polynomial in the standard basis and transform it into its representation in this alternate Lagrange basis? The intuition is quite simple. We have a polynomial p of x in the standard basis representation or the coefficient representation. We have the coefficients a sub 0, a sub 1, a sub 2 and so on up to a sub d. This is shown here by this column vector. So, our goal is to transform this column vector into this column vector y sub 0, y sub 1 and so on up to y sub d, which is vector representation of this polynomial in the chosen Lagrange basis. And in order to achieve this, what we need to do is evaluate the polynomial p of x at x sub 0, and when we evaluate it at x sub 0, we will get y sub 0. When we evaluate it at x sub 1, we will get y sub 1. And this evaluation can be achieved by the vector product. So, suppose for example, we want to evaluate this polynomial at x sub 1, what we need is the vector product of this row times this column. So, if we arrange these monomial bases evaluated at x sub 0, x sub 1 and so on to form this matrix V, and we take the product of V, the matrix product of V times this vector A, each of the terms that we will get in the right hand side is going to be an evaluation of the polynomial p of x at the appropriate x equal to x sub I value. So, this transformation therefore is quite clear that it can be represented by a matrix times a vector. This matrix has a very nice property. If you look at any of the rows, the terms form a geometric progression, and such matrices are called van der Monde matrices, and they are very useful because they are known to be invertible. So, this guarantees that when we transform a polynomial from the standard basis to the Lagrange basis, we also can this is a matrix times a vector. This matrix has an inverse, and so we can also transform the Lagrange basis representation back to the standard basis representation. We have already talked about the coefficient representation. There is one more way in which polynomials can be represented, and this is essentially the Lagrange basis. This other representation is nothing but the point value representation. We can for each polynomial of degree d, we will require d plus 1 point value pairs, x sub 0, y sub 0, x sub 1, y sub 1 and so on up to x sub d, y sub d. Now, all the x sub i's must be distinct, and this will uniquely represent the polynomial of degree at most d plus 1. And this is obvious consequence of the unique interpolating polynomial theorem that we have already looked at. Notice that the point value representation of the polynomial p of x is equivalent to the coordinates of p of x in the Lagrange basis. So, if you take the Lagrange basis defined, now this is important, it must be defined at x sub 0, x sub 1 and so on up to x sub d. Then the coordinates of the Lagrange basis are essentially the evaluations of the polynomial at x sub 0, x sub 1 and so on. So, there is a clear correspondence between point value representation where the x sub I values are x sub 0, x sub 1 and so on up to x sub d, and the Lagrange basis which is defined by the x coordinates x sub 0, x 1 and so on up to x sub d. So, we have seen so far that the set of all polynomials of degree bounded from above by d form a vector space, and this vector space will be of dimension d plus 1. We have seen two bases for this vector space. The standard basis is nothing but the monomial basis functions, and We also looked at the Lagrange basis for this vector space. It's a family of bases. Each Lagrange basis is built upon a selection of d plus 1 interpolating points, x sub 0, x sub 1 up to x sub d. And any polynomial can be represented in the Lagrange basis simply by evaluating the polynomial at the d plus 1 interpolating points. And we've seen that we can the transformation from the standard basis to the Lagrange basis and back to the standard basis can all be done via matrix multiplication, or rather a matrix times vector.